Professor Rushdie.
Thank you very much for your kind words. Ladies and gentlemen, let me remind you once more, here is about the scientific tradition in Islam. People who are interested in the question of revivalism and so on, it is not in this hall. Please, they can leave now to the other hall, please. That's clear? All right. The title of, I repeat once more? No, it is all right. The title of this talk, as it is written on the program, is the scientific tradition in Islam. It is not an easy subject, I say it from the beginning, and requires some knowledge in mathematics and in history of mathematics especially. The choice of such subject is motivated by the following reasons. Why I choose this subject. I have no idea about the exhibition. I have no idea about this manifestation. It seems to me, I asked it on the level, they told me that are university student and more. Then I will stay on this level. I try to come below, but there is, I cannot go beyond a certain limit. Good, why this subject? This subject, first, it is a way to show that science was an essential dimension of Islamic civilization. Not only religious disciplines, theology, jurisprudence, and so on, were the main dimension of this civilization, but also science. Second reason, science was present in the Islamic society. It was a real practice in the mosque, as well as in the hospitals, as well as in the observatories. I mean, it was a real practice in this society. If you give up science from the history of the Islamic society, you will not understand it. Third reason, rational values diffused by science. I mean by science, by mathematics, by physics, by philosophy, and so on. These rational values were among the main values of the Islamic society during at least 7 centuries. If it is not the case now, that is for other reasons. Finally, there is one more reason for this choice. It is, from a professional point of view, it is time to get facts right and to rewrite the history of mathematics and the sciences, and consequently recognize the essential contribution of the Islamic civilization to mathematics and to science. I pretend that it is the only way to understand early modern science. I mean, in a very concrete way, if you don't know what were the contribution of Khayyam, of Ibn al-Haytham, and so on, you cannot understand in a very accurate way what Descartes, Fermat, Wallis, and Huygens has done. That is the main reasons for this choice. If we want to resume this scientific fact in one word, we can say that science in Islam was the first universal science, in this sense that it was not localized in the east part of the Mediterranean Sea as the Greek science. I mean, as you know, the Greek science was almost localized in the east part of the Mediterranean Sea. With this scientific activities in Islam, science had, at this moment, the dimension of the ancient world, I mean from China to Spain. And this universality was acquired for the first time with this with the science in the Islamic civilization. What it means, this universality? It means it was universal, this science was universal by its origins. In this sense, there are Babylonian, Egyptian, and particularly Greek, and Sanskrit, Balhavi, All these branches were, all these sources was essential for the science in the Islamic period. Then you have this kind of universality from the beginning. A second thing, for the first time, all sources feeded the same science. It is all the sources, Sanskrit, Balhavi, Babylonian, and so on, feeded the same science. The second aspect, it was also universal by its community, the community of scientists. From one part, they were Arabs, Persian, Indians, and so on. Then for the first time, science was not the science of the upper class, it was of a dominant nationality, it was the science of all these nationalities at the same time. At the same time, you can find the Muslims, the Christians, the Jews, Sabians, all the scientists. For instance, Khwarizmi was Muslim, Thabit ibn Qurra, who was a very, very great scientist. I will speak a little about him. For instance, he was Sabian. Others are Jews. Many were Christians, and so on. That is also a new aspect of or new manifestation of this universality. Third, by its library. For the first time, we have a library, a scientific library, in which you can find Greek translations, Balhavi translations, and all the other sources in Arabic. Then, for the first time, you have a complete library, a complete scientific library in Arabic. Arabic was not, from this period on, Arabic was not the language of a nation or of only a religion, but it was a language of civilization, a language of culture, let me say all the culture at the same time. That is the fourth aspect of this universality is its extension. That this science was not only science for this period and only in Arabic, but there is the extension and the Hebrew extension of this science. If you take, for instance, books written by Latin people like Fibonacci in alias Leonardo Pisano in the 13th century, was the most important mathematician in Europe. His writing in mathematics are in the same style and following the same methods as in Arabic science, and that is, or science in Islam. That is what I mean by extension. You will find a very great movement of translation of this science in Latin during the 12th century, and also in Hebrew during this century. They will continue to translate in Hebrew until the 15th and 16th century. Now, to prove all this, we have to go to historical and the scientific details. Then, to make my talk more accessible, let me at first mention some names and introduce some main figures. That is the easiest way to speak about a difficult subject. I have a transparent, but there is no way to use transparent here. Then let me mention some names. I have no blackboard. Then I will pronounce it as distinctly as possible, and I will say some words before coming to my own subject. All of you know the name of Khwarizmi as inventor of algebra. All of you know the name of Khayyam, and all of you know the name of Ibn al-Haytham or Thabit ibn Qurra. Excuse me, as far as I have no transparent, I will go further. Then I shall try to give the main, the main aspect of this historical fact, what it means. Recent historiography seems to have permitted us to establish the fact during at least, this fact is the following, during at least 5 centuries, the intense classical research in science continued to unfold principally within the lands of Islam and in the Arabic language, as I mentioned before. Between the 8th and the 14th centuries, this research was accomplished by figures like Khwarizmi, who was the first to write on algebra, Ibn al-Haytham, to whom we owe the first revolution in optics and more generally in physics, and Khayyam, who was the first to conceive algebraic geometry, a new discipline, not known before, a new branch of mathematics. However, this intense, continual, and fecund research was not only conducted by isolated individuals as such, as we can read in the books of history of science, rather it was also undertaken by dynasties of scientists that constituted genuine research teams within established schools. I remind you, for instance, the Bayt al-Hikmah, the House of Wisdom, in which people, the 3 brothers, Banu Musa, all the 3 were very important mathematicians, as well as Khwarizmi was working in this Academy of Baghdad. I can evoke also the Maragha school. Maragha is in the north of Iran, where there was a very important observatory, and in this observatory in the 13th century, there was a school working on astronomy and mathematics at the same time. Then the main problem is, the main aspect is that not only individuals were working, but there were schools and the traditions who were working. To establish this fact, without giving neither an anecdotic representation nor a scattered picture, I propose to consider only traditions of research during these 5 centuries. I will not follow this method to say there was the portrait of one scientist and another in a very eclectic way. I shall try to elaborate the main traditions of research at that time. But due to my time limit, I shall restrict my accounts on the case of mathematics, which I propose to outline its principal traditions. However, to understand the emergence and the genesis of these conceptual traditions, I ought to recall 2 crucial events. While these traditions were in a state of gestation during the 8th century, they got produced in the centuries that followed. I should talk about the expansion and not simply the transmission of Greek mathematics into Arabic, and of the constitution of algebra as an autonomous discipline in mathematics. These 2 events, the translation of Greek mathematics and the Greek science from one side, and the constitution of algebra as a new discipline. In the 9th century and also in the 10th century, we witnessed a massive movement of translation into Arabic of great Greek texts in mathematics, astronomy, medicine, and philosophy. A superficial knowledge leads a naive mind to think that these traditions were established through a random discovery of books and at the caprice of circumstance. That means mainly people describe this movement of translation, which is a very important movement, as if they were working by random. But it is not absolutely the case. A systematic study of this movement, together with the translated text, allow us to establish that this enterprise was closely connected with an active research undertaken during the same epoch, which was sustained at first within the humanities and the social disciplines, linguistics, history, jurisprudence, speculative theology, philosophy, and then within the mathematical sciences. To understand how it began, let me remind you a very simple, very important thing. From the half of the 7th century and during the 8th century, the main disciplines which were developed at this moment were the social and social disciplines. Linguistics, jurisprudence, commentary of Quran, then theology, speculative theology, and so on. This activity of research in this discipline, which was necessary for the building of the new state and for the ideology of the new society, these disciplines, in a way, created a kind of a public interested in sciences and interested in rigorous, in mathematics and in sciences to solve their own problem. Let me take one example. For instance, for lexicography. That was in the 8th century that people, for the first time, a linguist, Al-Khalil, thought about how to write a dictionary of the Arabic language. That means how to create this new discipline, which is lexicography. Or to do that, he needed a kind of combinatorial analysis and a theoretical analysis of the language, phonology, morphology, and theory of grammar, and combinatorial analysis. So he can write his, he can establish this new discipline, which is the lexicography, all right? You see, from inside the linguistic, people needed to know more mathematics, that means the combinatorial analysis, to work in lexicography. As you see, the research in social disciplines and human disciplines leaded them to this kind of new research or this need for mathematics. At the same time, you have the development of theological school, speculative theological school, which were discussing also problems in physics, the problem of atomism, problems of causality, and all this kind of problem. For this reason, they were interested also in the translation of philosophy and of science. And in a way, the new public, which needed science and the mathematics, was created by this research from the beginning in the social domain. Afterwards, there was the need to translate the Greek legacy in mathematics, but what it means translation. Let me recall an instance taken from the career of a scientist, Thabit ibn Qurra, died 901, who represents an ideal figure of a mathematician who was also a translator. As a translator, he translated, for instance, Nicomache's book of Introduction to Arithmetic. No, excuse me, I cannot follow. I will stop. No, I cannot.
Sorry, can we ask, please, because it's very disruptive for the children to be here. It's very disruptive for the children. So can we ask, please, if I'm sorry to ask this, but can we ask, please, parents with children to leave this particular lecture, because it's very difficult, actually, for the professor to concentrate. Otherwise, he's not going to continue. I'm sorry to have to ask this, but
All right. Then I take just what means translation, scientific translation in this period. Scientific translation was not a passive way to translate from Greek to Arabic. Translators were themselves, the main translator were themselves very important scientists. And I will take one example, that of Thabit ibn Qurra. Thabit ibn Qurra died in 901. He translated many books in mathematics and in other fields, also in philosophy and in other fields. He translated a part of Euclid Elements. He translated a part of Apollonius Conics. He translated, a very huge work. What meant translation for this, for Thabit ibn Qurra? I take only one example. He translated a book of Nicomachus of Gerasa. As you say, you know Gerasa is in Palestine, and Nicomachus was a Greek Palestinian from this period. And he wrote his book, Introduction to Arithmetic. It is a book in new Pythagorean arithmetics. In this book, what you find only the definition of, for instance, amicable numbers. What is an amicable number? A couple of amicable numbers that means that the sum of divisors of one of the number is equal the other number, and the sum of the divisors, proper divisors, of the other number is equal this number. You take, for instance, 220 and 284. The sum of divisors of 220 equal 284, and the sum of divisors of 284 equal 220. That is two amicable numbers. Then, but there was no theory at all. When Thabit ibn Qurra translated this book, he invented for the first time in the history of mathematics the main theorem about amicable numbers, which we use until now. That means when he was translating, he was not just translating as a common translator of today. No, he was making research at the same time and developing what he was translating. This is not an exceptional example. On the contrary, you find the same phenomenon if you examine the translation of the most important Greek books in mathematics. I mean, Diophantus Arithmetica, for instance, Apollonius Conics, and many other, Archimedes on the measure of the circle and on the sphere on the cylinder. You find exactly the same phenomenon. And then from the beginning, this translation movement was in a way a movement of extension of Greek mathematics on the same level, in the same style as the Greek mathematics. As fundamental, that was the first event, translation. The second event was that of the constitution of algebra as as a distinct discipline and independent mathematical discipline during the first decades of the 9th century. There is no, I will not develop that. It is not the place here to develop that. But there was no algebra before this period. There were some algebraic techniques, but not algebra as a discipline. And this happened about before 830 by Khwarizmi. One of the consequences of the birth of this discipline that resulted from the novel ontology of mathematical object which it required was the immense and the previously unknown possibility of applying discipline to one another. I will explain. I don't know where I put my watch. No problem. Good. In any case, what I'm, all right. What I mean by that is the following. What is new with algebra is the following thing. The object of algebra is a formal object. That means what they call at this moment the thing, what we call today X, I mean the unknown. This unknown has a particular ontological position. That means what? This unknown can be at the same time an arithmetical object as well as a geometrical magnitude. If you take an algebraic equation, the unknown can represent at the same time many things, but at the same time arithmetical entity and a geometrical magnitude. That was forbidden in the Greek mathematics. It was impossible. There was, for the geometry, there was the techniques for the geometry, a way to prove, and so on. And for arithmetics, it was a separate domain. We cannot use the same techniques inside. Then for the first time, you have a discipline which subject can be anything else as an object of mathematics. That was very important in this sense. It permitted the application of discipline one on the other. Then that was possible now to apply algebra on arithmetics, to apply arithmetics on algebra, to apply algebra on geometry, to apply geometry on algebra, to apply algebra on theory of number, and so on, and to apply algebra on geometry, trigonometry, and so on. What does it mean? It meant the following thing. Every application was was a creation of a new chapter in mathematics. When you apply algebra on arithmetics, they created the new polynomial algebra, which was known before and which was not known before. And this polynomial algebra had this important aspect that it permitted the creation of abstract algebraic calculus.
Attention, please. This is an urgent security message.
And
the driver of a blue Celica W526 GAP
I don't find any more
parked
in
at
my
the
work.
front of the building. Please return to it immediately. I repeat, the driver of a blue Celica
Well, no problem.
parked at the front of the building. Return to it immediately. Thank you.
All right. Then this new chapter, which is the abstract algebraic calculus, you will find exactly the same result at the end of the 10th century by Karaji. You will find exactly the same result later on in the Italian school, for instance, by Bombelli in the 16th century, and so on until Vieta in the end of the 16th century. Then there is no new techniques after Al-Karaji on this domain. That is one chapter. The other chapter was the following. When you apply algebra on geometry, they created what we call now the elementary algebraic geometry. How it was created? In the following way, they were unable to solve by radicals the cubic equation. Then they had to solve the cubic equation, but not by radicals. In this sense, they used conic section to solve the cubic equation. If some of you who know that if you take two conic sections, then if you translate the conic section in algebraic way, you can have a fourth degree equation which can be reduced to third degree equation. And in this way, they solved all the forms of cubic equation. Then, as you see, there is two movement of translation. Translation of the Greek, of the geometrical magnitude in algebraic equations, and at the same time, the translation of the algebraic equation in a geometrical, with the help of the conics, to determine a positive root of the third degree equation. And that was the beginning of this, algebraic geometry. What is very interesting, what Khayyam, who invented the theory, the first part of the geometry of Descartes, what Descartes had done until 1630, at least 1628, but 1630, is less than you can find in the book of Khayyam. And in the book, the very important book of Descartes, which is the book which defines modernity in a sense, which is the geometry, the title is the geometry, La Géométrie. In this book of Descartes, you have two dimensions. One dimension is exactly the program of Al-Khayyam. The other dimension is not the program of Al-Khayyam, it is the study of equations, the study of curves by their equation. But that is another question. But what I mean that the one half of the project of Descartes was already done by Khayyam. It doesn't mean what I try to say that Descartes was not original, not at all. Or Descartes was not important, not at all. I try to say only that if you want to understand this early modern mathematics, the 17th century mathematics, if you don't know the book of Khayyam on this book of Khayyam on algebra, you cannot understand in a very accurate way what happened before, what happened later, because you will think that all was invented by Descartes, but that is not true, and you will not understand what is the main point in Descartes' geometry. This, I have time left? All right. This, I mentioned now two traditions. The algebraic, the tradition of abstract algebraic calculus with Karaji from the 10th century on, this other tradition of algebraic geometry. There is many other traditions now in theory of number and on what we call indeterminate analysis. You see, there is the book of Arithmetica of Diophantus, 2nd century perhaps, from our area, from the Christian area. In this book, there is many problems, determinate and indeterminate analysis. But Diophantus gave only one solution for an equation is indeterminate if the number of unknown is more than the equation. If you have, for instance, equation of the kind ax plus by equals c, that is indeterminate equation because you have two unknowns and only one equation. Then you generalize that on systems of equations and it works. What I mean by that is the following. Then in the 10th century, they invented, to be clear, Diophantus looked only for one rational solution. From the 9th century, mathematicians developed this rational Diophantine analysis or rational indeterminate analysis. And it became, from now on, a chapter in any important book of algebra. Then you will find, for instance, and this tradition will continue until Euler and Lagrange, until the 18th century. But in the 10th century, something new happened. mathematician like Khazin, Al-Khazin, wanted not to have rational solutions, but integer. Now, integer, that means in integer numbers. And that is more difficult. And in this way, he created what we call integer Diophantine analysis. I mean, Diophantine analysis in which we look for integer solutions, I mean solution with integer numbers. And that is a very important part of theory of number. This work of Al-Khazin, you find, this work of Al-Khazin, you find it once more, it was borrowed by Fibonacci in the 13th century, and it was transmitted in the Latin tradition until Fermat. Then that is another tradition. There is many names and many books and so on, but that is another tradition of research in this of mathematics in Islam. There is many other traditions in geometry, which I will not mention anymore. To conclude, I will say the following. We find analogous configurations with optics, astronomy, and statics, namely with all the different branches of classical science. Returning to our horizon, science in Islam presents itself as what it always was, namely as one of the constituents of universal science, as a part of the universal science. This presentation has doubtless been overshadowed by ideologies put forward by all sides of the debate, those of narrow-minded nationalism, as much as those of colonial ideologies, ancient and modern. And if we want to get the facts right, we have to have another look, to look at this science as a part and only a part of universal science. Thank you.
Thank you very much to Professor Rushdi Rashid for that presentation of scholarship. So we have just a few minutes for some quick answers, or quick questions or comments. So are there any? We have a microphone, I think. Do we have a microphone? Yes. Anyway, first of all, are there any questions? There's a question here. So do we have a microphone, please? Stewards? Could you put your hand up? Right. So we don't have a microphone.
You have nothing.
Okay. Do you want to stand up, please, and give your... We'll just wait until this microphone is switched on. Yeah.
Thank you. It was a very interesting talk of yours. In your opinion, from such a distinguished history of Muslims and the Islamic civilization, why is it that today Muslims are effectively ignorant in these disciplines?
In any case, there is external reason and there is internal reasons. And it happens that internal reasons and external reasons were combined at the moment. The internal reasons are the following: that there was a development, this development needed once to create from inside a kind of symbolism to go further. Good. If you take, for instance, a third-degree equation with imaginary roots, all right? If you try to do that with words, it will take around 50 pages to discuss all the possibilities. That was an upper limit. You cannot go further without a new symbolism. these samples was not created. They stopped there. But this internal reason could be surpassed at this moment if the external reasons were there. I mean, what were the external reasons? That was the economic and social development and interest in science. But it happened at this period. We are around 16th century and the beginning of the Ottoman Empire, which was oriented in a way which was not really, I mean, oriented in a way in which science was not a priority. And you know what happened afterwards. I mean, the discovery, the geographical discoveries, and all what happened, which make from this society a kind of more or less underdeveloped society, and the history continued like that. I mean, I don't know if I answered your question,
Okay.
Is that
but please.
Sorry.
leave
We should go to another.
so? What you're saying is that the main reason is because it's the governance of these communities didn't place an emphasis on science.
That is, yes, that was,
that's the main reason.
I mean, there was no any more economic and social expansion.
Any other questions? Okay, gentlemen, could you pass the microphone, please, to the gentleman?
Alaykum salam.
My main question is that as far as the modern science goes, the fundamental premise on which the science operates today is the scope of reasoning, that is the question of asking why and how, is limitless.
Why and how?
The scope of reasoning, you can question anything. That is the premise of the modern science and the scientific development of today. Am I right or not? You mean
I
in
didn't- I
scientific
didn't get
inquiry,
it.
in scientific inquiries and investigations, there is no limit to putting questions.
Yeah, there is no more?
No limit.
No, there is no limit, no.
Is it true?
Ah, yeah, absolutely,
In Islam,
yes.
that is not the case. Am I
In
right?
Islamic society, you mean?
No, Islamic science, the way the Islamic scientists came about, or the researches that was carried out at that time, the scope of the reasoning were not as limitless as it is in today's science. Am I right to understand? Or?
But, I mean, at
Because
this pe-
Islam has always been, is always based on a premise of certain fundamental and principles and ethics, beyond which there can be no questioning. Am I right to?
of this period, during this period from the 8th to the 15th century, there was no limit for questions.
It is the same as the modern science.
Yes, there was no limit, absolutely no limit for questions.
And that would be true even according to the strict Quranic and Islamic teachings?
I mean, it is more than true. I mean, you are asked to do it.
Because if the scientists, if the Muslim scientists have
Yes.
proceeded on the same premise as today's modern science, is the Quranic?
What is the contradiction? Where is the contradiction?
No, I'm not saying. I'm saying, is it the same? You know, similar. They're the same premise of.
I don't find any contradiction.
That's okay. Then. Okay.
The questions are infinitely open.
Right. Okay.
If not,
We'll take one last question.
Okay. Thank you very much.
I'm sorry, can I pass it elsewhere? One last question. So, the lady over here. Thank you very much.
Thank you, Professor. I'm not a mathematician, but I learned a lot, and I'm sure many of us would like to go and find out more. I just wanted to know, during that time when there was so much going on, obviously the society was doing economically well, and there was encouragement for that. What was the contribution of women at that time?
There is there was a contribution of some even in theology. Even in theology. I mean, one of the best theologians was a woman at this period of time. Then there is this aspect. But in science, in mathematics, for instance, there was no contribution for reasons that you know better than me until when? Until Sophie Germain. I mean, until the 19th century. I mean, but that is a social problem. You have to work for it. We help you. But
I hope, thank you. I think for the last few centuries in Islam, I think women have been slightly marginalized. And I do hope.
Not only in Islam, madam.
Yes,
Not
you're
only in
right.
Islam, everywhere.
Absolutely, it's a man's
Everywhere,
world.
yeah.
And I agree with you, but I do hope that now there is a lot more questioning, and I hope that women will be encouraged
Good.
to be people like yourself.
That has nothing to do with mathematics, but in any case, that cannot be independent of the rational values in the society.
Absolutely.
If you don't defend the rational values in the society, nothing will happen.
Thank you.
Thank you very much. I'm afraid I'm going to have to bring this to a close. So thank you especially to Professor